Welcome, whoever is there on board for the 9B session. As I explained, we will see what are the hyperparameters, why do they call them as hyperparameters, and what are they, and we will extract them using Python program and create a string of float values. We'll stop with that today and then use this string of float values for us to fill it into a C float array and then use it for extracting this information on ESP32. Okay, that is what we will do tomorrow. I will give you the flow of what needs to be done tomorrow so that finally we will be able to run a model what we develop here on TensorFlow using Keras on ESP32. That's our goal anyway, part of IoT course. Okay, before I go into the details of extracting out, let us understand what are the parameters we are interested in. These are the parameters which are the variables that govern the training process. Okay, the hyperparameters are something to do with the training process, not during the inferencing. So let me, if I have to define or compare the training versus inference, I would say this is equivalent to a designing a car, designing and building a car. Okay, equivalent to designing and building a car. Inferencing is something to do with driving the car. While driving, we should know where the clutch is, what are the way to operate it, how to read the speedometer, and know how to apply brake, that instructions, and how to change the gear. We need to know, of course, for driving, how to use the car. It is also complex enough that if you don't use it properly, we can get into some trouble. But designing and building a car is much more involved. It involves a lot of knowledge about different aspects of building the car. So you don't need to know everything while driving. You need to know how to control the car, how to achieve what you want, maybe direct the car to the goal destination. That's what you need to know while driving. So inferencing is something as simple as driving a car. Don't take it as a exact equivalent, but the complexity wise, training is much more complex and involves much more effort in coming up with a model. Not only coming up with the model, even doing the training, we need a powerful CPUs or GPUs to decide the hyperparameters of the model. So it needs lots of performance needed, and we need the CPU power to execute the model that you have and train it to the extent you want. And finally, to use it on inferencing is as easy as driving a car. So now what are the hyperparameters? There are basically, it is used during the training. It impacts the performance of our machine learning program, and proper selection of parameters is very important, and the job of doing it is called hyperparameter tuning or hypertuning. There is a separate tool as a part of Keras available to perform this job. Right now we are not going to do that. We are going to do how to see, maybe at the very top level, how to manually do a tuning of the model. That's what we are going to see here. Now we have already done some part of it yesterday, last class. And then there are two types of hyperparameters. One is related to the model, which influence the model selection, like how many layers you want to have, whether it is a dense connection or sparse connection, whether how many nodes are there in each layer. These are the things we decide about the model parameters, which are all related to the model. And there are something to do with the algorithm that is running on them. Now we know that in each of those nodes we will have different activation function. It could be sigmoid function or it can be a simple ReLU function. So how do we choose one of this? And then what loss function you want to have. We saw few of them, MSC, MAE. So we need to choose this loss function because which is going to impact the way the gradient computation is going to be done and the way the parameters are going to be modified. So deciding the number of parameters indirectly, that is what we do in the model hyperparameters, because they decide the number of parameters finally we'll have, and the algorithm hyperparameters are something to do with how do we change the specific functions to fine tune the parameters that we have chosen. So how to make the network learn. So that's part of the algorithm hyperparameter. So there are two types. Learning rate is one, loss function is one. Whether which one to choose, MSC or MAE, those things fall under the algorithm hyperparameters. Now, while writing the program, we need to keep that in mind and define some constants in Python words, and so that you can modify it in one place and the rest of the program works without any problem. So we need to at least have this many parameters based on what you are going to use in your model. So that's what we need to do while developing the program. And Keras tuner is something, a library which helps in tuning the hyperparameters. So with this, let us go back to our code, and then I have made a few changes compared to what we have used in the last class. I did not want the number of nodes in each layer to be given as a constants, magic numbers in the program. So we will define it as a constant variables here, so that in one place they are all captured. So you may see that it's a dense connection. So I am saying dense size, and earlier we had only 16, then we modified it to 32 nodes in the first layer. It is same problem like sine wave problem that we took earlier, and then I am trying to add one more layer to it, which are of 16 each, and then I have given a big number of epochs. We will modify it based on what we see in our program. Then samples are 1200, and seed I have already explained, and we have the function which is sine function from 0 to 2 pi. We are going to have a complete cycle of the sine wave. Then this one thing I wanted to mention earlier, we are using 0.01 here, 0.001, which is a very smaller value to the random number that we generate. We are multiplying it, which is of shape y shape. Okay, we are going to have a x value, which is an input 1200 entries. Y values are going to be computed from the x value of 1200 with applying sign, and then we are going to add some multiply some noise to individual values, so that we get a distributed value around the sine wave. So since we are choosing a very small number here, when we draw the picture, we did not see that it was distributed around the point. But if you have modified this to 0.1 or something, you will see a very wider spread of the y values around the sine wave. Okay, this also affects the training cycles. Actually, if you increase the noise in your input, you may have to train it for long. So to reduce the number of times we need to train the node, train the network, I have made it at a very small value, but I would like to modify this to a larger value and see the effect of your training and the output that you get. All that will get disturbed if you have a larger value of noise added. Okay, and then we know that test and validation we need to do. And then last class we had only this entry with 16 here. Now also it is 16. I am adding one more layer to the earlier layer. If you keep adding it, it is default assumed that it is going to be connected to the previous layer because it is a sequential model we have chosen. That's why we need to give input only here in the first thing, because the input is coming as a single input because it's a regression model, not a classification model. So we are going to predict the value of a continuous function. So an input is fed to the first layer. So that's why we are giving a single dimension array of values, which is supposed to be 1200 in our case, where we are going to take the samples from. Now, the second layer, we don't mention the input shape because we are mentioning it to be a dense layer. So all the previous layer output is going to be connected to every second layer nodes. So once you say that we have those many layers in the first layer, those many nodes, then second layer we say that it is a dense connection. It is implicit that we are going to connect every node output to every other node in the second layer. That's why we don't mention what is the input here. And then this is also very deep, very straightforward. When we say one node, then that is going to be the output node, and that output is given as a single node. So that's very obvious. Then we learned about what is RMS prop, and MSC is the loss function, and MAE is our metrics. Now these are the things right now. Then what we do, we are going to train it. This is where the training happens. Actual construction of the network happens here, and we are deciding the optimizer. Everything is done here, but still the hyperparameters in the model are all not initialized to any or trained also. It's not done. That we are going to do only here when we say fit the model with the input X train and Y train. So we are not going to feed all the 1200 when you are training. It is only some 80% or 60% of that value based on what we have chosen. That is what we are going to give as an input for training, not the full 1200. Epochs we have decided as 1600, I think. Then batch size is 16, which I already explained. Then once we do this training using that number of epochs and that many number of batch sizes, then we get the model which is available as a history too. Then we do a validation on that using, that's why we call it as validation data, where we are feeding in these two set of parameters which we have extracted from the 1200 samples we have, and that we are going to validate here and plot it. Okay, that's a summary of what we are planning to do. So let us now run all of them. I will not run it. So it is going to take more time because we are, I think, 1600 or 500. 1500. Okay. So let it run. Now in this meantime, I want to see if there are any questions anywhere. Okay. So let me come here. While that is getting trained, let us go forward. What I want to do is this class. This is already done. Now we are planning to extract the weights and biases. That means once we have so many nodes, now in our case we are planning it the 16 and 16. Okay, we know that each of them are having biases and so many inputs are there. I want each of those weights of connections to be extracted out into a floating point array. Okay, a floating point array with some floating point numbers followed by f. Suppose in C we want some number f, and then we want to give 3, 5, 6, 7, 8 some f. So we want a variable which may be an array of bias, maybe array, and then we will initialize it with whatever is the number of elements in that. It is decided by the number of nodes in this. So now we need to know how many parameters are going to be there, which all of you are aware of how to get that number based on the number of nodes we have in each layer, and then the dense connection we have. We are going to get as many number of hyperparameters. So once we decide and extract these values, we can actually do the inferencing, because once the training is done, as I told you, that deciding these numbers are very important and very crucial, and performance very computation intensive. Once this is done on ESP32, what we will be doing is, let me explain what we want to do in ESP32. That is a very low-end processor. It's not as complex as at least our Intel processor that I am running on. So what we want to do is, once we know the parameters extracted out, I want to actually port the complete model. Okay, not the tiny model or a TFLite model. Okay, in this case I am not doing this. First I want to actually do complete model that we have developed in Python or in the notebook. I want to put it on our ESP32. That means we are going to construct the same model. Okay, only thing what we do here is, only we will pass the input and we do the inferencing. We don't try to do any back propagation or any training here on the ESP32 because we want a trained model here. So on inferencing, what we are not supposed to do, we should know what is the input value, that x value that we need to compute based on the sine function. Okay, or we not the based on sine function. 0 to 2 pi is our input, so we will decide some number and then we will feed that to the model. Then we will know that 1 to whatever weights are there for each of those input to be multiplied with each of those layers. If in our case, if it is 16, we will have 16 weights. So this 16 weights will be in some array. We will multiply that with those input value. We'll add them out. We know that it is a sigma. We'll add all of them. And then bias, we will have another array. So we will individually, we'll add all the values. In our case, first case, it will be our single input. Then we'll add the bias. Then ReLU function. ReLU function is nothing but the thing is like this. So this we can implement it using max of x, 0.0, x. This way, same thing we can implement in C. So we will do the ReLU function also implemented in C. We will do whatever the model does when the input is given. We will do it in C program, so that you know exactly how the model is getting executed during the inferencing time, not during the training time. Training time, if you want to know, you need to know the back propagation and that logic we need to implement. That we are not trying to do. We are doing only the inferencing part. Then all the other intermediate nodes we will know. Then finally, whatever output we get, we can plot it on ESP32. That is our plan. Okay. So any doubts you have, let me know. Before that, let me see whether output is ready now. So most probably it must be ready. Okay, this is shown as very clean waveform because this range is between -1 to +1. But if you increase that 0.001 noise to something higher, you will get that this is spread across. Okay, so that is not a problem. Now this value, I am sure you will be able to find out because 16 by 16. Let me explain in case if you guys have doubts. Okay, this is enough. We are giving 16 here, 16 here. That is our model first. Then this is input and this is output. Okay. So how many will be there? 16 will be there, weights, because all the input is same. Input is coming to all the nodes. And then all these nodes will have 16 biases. So this will add up to 32. So this layer, 32 hyperparameters. Now what about this guy? Here there are 16 into 16. Okay, 256 plus, because all 16 outputs are going to all 16 input nodes of the second layer. So 16 into 16 is there, 256 weights will be there, and then 32 biases because all these nodes will have one bias. So there is 32. If you add it, it will be 8. Now you can add it up. Then we will have, okay, we will add it and see how much it is coming. Oh, sorry, 16. Okay, so it will be 272. Okay, it's not 32. 256 plus 16. Okay, so now what is going to be there? This is going to be output to all. Okay, this all, there will be 16 output. So 16 plus 1 bias for the last output. So that is 1. So that will be 17. So we know that these are the number of hyperparameters. And remember that ReLU function is here on these two, whereas there is no ReLU function here. It should not be there. And whatever is the output we get, we'll add the bias and then is the final output we get. So this is clear. And then let us go forward. Okay, now I am printing the loss. Now this is what we are going to do a tuning now. The error is, this is the error between the validation input and the training loss. Training loss is what we gain while during the training. Whatever the loss we are getting is what is plotted. As and when every epoch the biases and weights are updated, we also measure the loss using the training input. that mean square error. And then we also give a validation input on those models on during the epochs and see how it behaves for the unknown input. See, the blue thing is for the data which is not seen by the model, whereas green is the error that we get by the model for the seen data. This is all trained data, whereas this validation data is something different, different samples. So we want to see how it behaves when unseen data is given. So it is more or less the difference is high during the initial stages because the model has not converged, and during this epoch between the maybe 700 to 800 epochs, there is a drastic improvement in the model weights and the biases. The loss has come down drastically and it is remaining almost close to zero. Now from 800 we don't see much of improvement, so we can also afford to reduce the training epochs so that we can save time on the training the network. Okay, so from this we can make out, and we can also, the same behavior is happening here also between the expanded version. Okay, we are just showing it with a few data points. We want to see how it exactly spread across. Then this is what we are getting. Now you can see that the negative peak is not exactly same as what we see in the original signal. There is a straight line there, but we are okay to live with the noise, assume. Okay, so how do we improve it? I don't want to train so long, so we can actually change it to maybe 900 because we saw that after 800 there is not much of improvement. So maybe we can keep it as 900 and then train it. Okay, I don't want to run it again because it is going to be the same. I want you to do it because to save time I am going to cut short this time. What will happen is you will see the same picture. Only thing is it will not go further, it will stop at 900. Anyway, it is better here, it's not going to be much of a change. So we will see the almost similar waveform for 900. Okay, so let us, maybe I will run it and then come back here. Now before doing that I want to do something. I want to explain you how to extract the parameters. Now with the 16 nodes in each layer it is going to be complex, so let us change it to some smaller number, 5 nodes. Okay, this is only for experimentation purpose. I am going to make it as 5 nodes. Okay, the purpose is not to see the output, it is purpose is to extract the weights and biases. So let us do that. Now I don't even want, I'm not interested in the output, so I don't need to train it for so long. So let me make it as 100. Okay, and batch size let it be 16, no issues. We are not going to change anything more. Okay, only we are going to change these things. Okay, and then we will run it. So I will run it with these values, and then I will show you. You should not see the output because it will be very bad. So let us see what happens. 100 only, it will not be too much. So let us see the output. So this is the output. Okay, now I want you to tell me why are we not seeing any output at all on the training. Okay, here we are seeing this. Okay, but I don't see any plot here on this. Okay, to just help you out to find the reason, what we have chosen is batch size happens to be 16, we chose. Epochs, number of epochs we chose 100, and then number of layer 1 nodes 5, layer 2 nodes 2. Okay, now my question is, two questions I have. First of all, why I don't see any output at all in this? Okay, that doesn't mean that there is no noise here, but I don't see any output. Maybe you can answer that question first before I ask you the second question. Anyone can come online, or you are answering on this. I don't know. If I go there, you will be disturbed. Okay, good. Okay, you are already answered it. Fine. You are very attentive. So, yeah, we are skipping the first 100 data points, and we are training only for 100 epochs. Okay, yeah, it is epochs, 100 epochs. So we are skipping 100 epochs and we are training the network only for 100 epochs. We have no data to show, so we need to comment off this. But remember it that you are to undo it when you are doing it with the other numbers. So okay, that is a good point. Now I have one more question for you. Why are we having all of them here? Okay, you may say that it is because we are training it for only 5, we are having only 5 nodes, not even 16 nodes, the bad values. Okay, but it remains to be almost 0. It says that error, the predicted value remains as 0. And if you see, maybe I will run it. Okay, I need to run it with a skip value removed so that I will show you something more. Okay, now let me show the output. Okay, now we are seeing this output sine wave. The predicted value is just remaining here. Okay, why I'm not getting any output at all? Oh, sorry, I should not put skip is equal to 100. I should make it as 0. Okay, then I will get error here. Okay, I should put 0 and then train it. I hope you got it. Okay, otherwise I'll get error because skip is not defined. Okay, you need to initialize it to 0. So because I have the constant defined already, so that's the reason. Okay, now my question now to you is, initial stages model is very bad, error is 3, maybe based on the random values of the weights, and it is settling down to 0.5. Okay, it is settling down to 0.5, error is only 0.5, but the output is still bad. It is not even close to any of the sine wave. Can you tell me why, if you look at the value, error value, it's only 0.5, but the output predicted graph is too bad? If it is only 0.5, why is it so bad? Any idea? Anybody wants to take here? MSE, okay. That doesn't answer my question fully. You are right, MSE is fine, but okay. How do you, okay, you are not coming down, okay, but average will always be around 0.5. Okay, yeah, you are right. The reason being, the maximum output itself is 1. Okay, and the error can be maximum 1 here, and the maximum error could be -1 here, and the average is 0.5. So that's what we are getting. So similar to, if you guys are from electronics background, you know that the RMS value, okay, the RMS value of sine wave is what? 230 volts, whatever we see in our homes. Let me explain. The 230 volts that we see, okay, is it RMS value or is it peak value, peak to peak of our sine wave? Is it this value or is the RMS is this value, 230 volt? Peak to peak or maybe 0 to peak. Okay, is the peak value is 230 volts or is it the RMS value is 230? I hope you guys know it. Yeah, RMS. Okay, so now if it is 230, how are we getting a number which is non-zero value? Okay, because if it is equal sine wave, it should, whatever average value you get here, positive value, the same average here is negative. If you took an average of a whole cycle, we will get 0 here. Okay, so effectively the RMS value, when it is computed only for the half sine wave, not the full sine wave. Okay, so that's the reason we get something which is decent enough value, which is called 230 volt. And one more, yeah, go ahead.
Sir, actually, it could be also we can say that basically we are taking the point, we are taking every value on the curve and then we are dividing it by 2 pi. So it is area under the curve divided by 2 pi. 2 pi.
No, but when you compute the integration of this graph, you are going to get this area, right?
Yes, sir. Positive.
Negative.
Will do.
Yeah, yeah,
Will take 2 into.
yeah. We need to actually what is happening in our sine wave computation in our AC circuits is we only take the half cycle of the thing. Okay, effectively the 230 volts is nothing but the power that to deliver or heat generated by the DC voltage, which is equivalent to 230 volts. Okay, that's maybe I'm digressing too much on the electronic side. Okay, fine. Now, what I am going to do here is to just to show you a different perspective of the input. I want to generate not the full sine wave. I want to generate only the half sine wave. Okay, how do you do it in our code? Where do you think I should change it? I want to only generate a half sine wave. Okay, it's like a half wave rectifier. Can you tell me where should I
So,
check? Yeah,
so we can modulo pi.
yeah, modulo pi is output. Actually, what we can do is the output what you get, you have to be modulo, do a abstract absolute value so that negative all become positive. Other option is to change the range of values that you have into either just okay pi. Okay, you only change it from sine 0 to pi. That's the input. So input itself is going to be only this much. So I am not even generating the other half of the wave. So let us see how this model behaves with the 5 nodes as a first layer and 2 layers. And I am just, please remember, I am changing all this. So you need to know how to undo it when I am sharing this code with you. Okay, now I am going to run it. You can see that we are only feeding the value from 0 to pi. So you are having only the half sine wave and we want to train it and we want to see how the behavior of the noise is going to be. So this is how the noise becomes, and now you see that the noise is not even zero point 0.5, it has gone down to even 0, almost close to 0. Okay, this is the output of the noise that you get, and this is the signal output predicted value. So our model, even with the 5 nodes as a first layer and 2 nodes as a second layer, if you are giving only the positive cycle, we can get a decent estimate of the sine wave like this. Okay, it's not even sine wave, but it's like a triangle now. So I want you to try it out different values and see can you make sense out of what you are seeing and based on what you give input. Okay, fine. Now I will not go deeper into this. Our main aim is to extract the output. So let us see the code, or okay, let me explain it here and then we will go there. Okay, so hyperparameters we are seeing extracting the weights. After having successfully constructed a two-layer model, we want to study the perceptron. Okay, perceptron is nothing but the mathematical model of the neuron. One major difference between our human neurons and the perceptron is, in our perceptron here in sequential model, we expect each of this supposed to be equivalent of neuron in our brain. Okay, synapses and other nerve cells and other things. Okay, but one major difference between the neuron connection and connection that we have in our neural network is that we are only connecting the layers just above with the lower ones. Okay, these neurons are not, so multiple layers are there, they are only connected to the only adjacent two layers. Whereas in our brain, if it is like this, we will not be even able to walk on our road, on the road. So we, in our case, in our brain, the neurons are connected, multiple connections. It is not going by layers of the neurons. Multiple connections are there. Whereas to simplify our implementation, we have just taken the idea from our brain and then simplified it so much that we cannot even call it as a neuron. So we are calling it as a perceptron. Now we have simplified it further to just see how we are going to extract the output of different layer weights and biases. So if we are going to have only 5 layers here, 2 layers and one output layer, there is no node as an input node. Okay, there is no node. Actual the input is fed to all of them after multiplying with the weight. So this is the output. So very simple to find out these values. I am not going to explain. Now one just clarification, this none is given here to say that the output shape means a new dimension is added to the list. Okay, it is like we are giving 5 and none means we have one data which is a list. Inside that we are going to keep these weights or whatever the values 5 and 2 as additional another list. Okay, a list inside a list, it is internally maintained like that. So that's why it's showing you the output like this. Okay, now let me go to the program now. No, I will see here only, I will show you here only so that you understand the output. Okay, now we want to know what are the weights of these values. Okay, so these are the weights. Okay, I will show you the code which is extracting out. These are the values of weight after getting trained. It is as a how many entries we have. In this case, we have 5 weights, each of them. Okay, these values are given as this. Okay, this is the first connection, this weight, and then this. Okay, 5 values. You see that these values have been derived by our backpropagation algorithm. Okay, fine. Now biases. What are the bias values of each of the nodes? These nodes, each of the bias values are given as these values. Okay, now how many you will have here? 10, you know that. So how do we list it here? Okay, this is very important. We will see that later, how it is listed. Now see here, these are 5 values are there, and then the same value with a different weight is multiplied. Oh, sorry. Okay, it is coming here. Okay, this. So there's like this. Different weights are going to be multiplied for this guy. Now it is listing out in this way. Okay, that means these weights. Okay, if I call it as maybe W12, W13, sorry, 11, 12. If I'm calling this as a I is changing from 1 to 5, and J is changing from 1 to 2. This is J. Okay, this is J, which is changing from 1 to 2. Assume I am not 0 to 1 actually, but for our easy understanding. Now it is listing out the 5 values in this way. Okay, so this corresponds to this value, which is first node, and the second node coming here, this value is corresponding to this. Okay, so that is how it is listed. Okay, 2 each. So that means this is for J1, this is for J equal to 2 for this node. Okay, these 2 nodes. So in case if I had 5 here and then 3 were there, sorry, not okay, 3 were there, we will have one more column added here, and then we will have those entries. Okay, this is how internally TensorFlow is maintaining the constants. Okay, weights. Okay, it's in our case it is a weight. So we will see the code to extract them out, and bias is just a 2 values. Okay, again the bias is like this, only 2 number of nodes, or how many nodes are there. Now what about this? How do you see this value to be? It will be like this. Okay, it is little different from what you see here. Okay, it is again showing it as column matrix. Okay, and this output, this weight is shown here. This is the weight, sorry, first entry, and this weight is shown here. Okay, so if you want to extract the weight, we should know how internally it is maintained so that we can extract it out. Okay, so bias is just one entry here. This is also having a bias. Okay, now I hope this is clear to you. Now let me see what I have. Okay, that's all. Okay, this is the output. Now how much time I have? Okay, 5 minutes I have. let me explain, and then we will take it up tomorrow. I will share the code also to you so that you will have time to go through it. Now, what I do, model 2 is the model we have created it. Okay, that let me show that. Okay, model 2 is what is returned by. Okay, here model 2 is what we have constructed here, sequential model 2, and we use adding those things to this. I am calling it as a model 2 just to say that it's a 2-layer model. Okay, initially model 1 we had, it's a 1-layer model, so model 2, and then I'm going to ask you to do a model 3 yourself as an assignment. Only one assignment is going to be there, which is little bit involved. You need to understand this code to generate the model 3 code. Okay, now let me explain what I am doing. Model 2 I am doing it as a model because this code I want to use it, for model 3 also. So it is easier to have it as a single value model. And then layer 0 get weights. So when you say get weights, it is not even getting the weights, it is also getting the bias of that particular layer. So let me explain. When you do layers, model layers 0, it actually shows this is the input and this is the whatever layer we have. This bias, okay, B1, B2, B5, and then this weights W1 to W5. These values are coming out as kernel. I gave it as a kernel 1. This I call this as a first layer. Okay, first layer. Whatever I associated with this first layer, okay, this is the first layer. Whatever is associated with the first layer, we extract it out as kernel 1 and bias 1, and we need to have a index as 0. Okay, so I hope this is clear. Where is the, okay, fine. Now this is what I am printing it out. What I showed you, the output is maintained like this. Now let me show the output that I showed you. Okay, it is actually maintaining as a list inside a list, right? A list inside a list. So this layer is having a list inside a list. So what I should do, if I want to extract out it is having only one list, okay, and these are all the elements W1 to W5, okay, because I have 5 elements, 5 weights. Now if I want to access it, I should first access the list object, which is the 0th element of this list, and then the individual elements are this, right? So what I do, I need to get to know how many are there, because your extraction routine should be independent of what you decide there, okay, in the generation of the network. So go with the actual length that you get out of this. So make it generic enough so that this code can work. Whether you change this to 16 or 32, it will still work. So what you do, access the inside list kernel 1 of 0, which is nothing but the internal list object, get the length of it. So that will be 5 here now for our case. And then I am doing extracting the 4 values first. Okay, I'll tell you the reason. 4 values I am extracting out. How am I? By -1 I am doing. So 0 and I. That means we are extracting out the kernel of 0. That means we are accessing this list, and then up to length -1. That means including 4 I am taking values. These values I am extracting out and printing it out with a f value. So I want to print it out as 0.25f, 0.3f, something like that. Okay, floating point values. Now if I want the last value also to be printed with the f, I have to do it in an individual way so that I get it out. Okay, because the reason is I want to put for the last value, I want to fill a return parenthesis, because I want to actually create an array of floating values. Our intent is to use it in our C library. So the last f when I put, I need to put this closing parenthesis also. So to do that, I am now extracting out the last value separately. Okay, that's all. So this is what I am doing. And bias also I do the same thing. In the bias case, it is only a list of values. Okay, just a direct list only. I don't need to find out the internal list, so I can extract it out separate, directly. Okay, so this code is very straightforward. Same thing I do for, not same thing, I need to do little different for this one. Okay, now let me show the output so that you understand what exactly is happening here. Okay, this is the list we are trying to access. It is stored in this way. Okay, list inside a list object. So I am just extracting out the value. My aim is not to it's a flattening out. I am flattening out. Okay, so this value followed by this, and then this, and followed by this. I will add a f to it so that I get a list of flattened values of weights. Because it is a second layer, we have a two connections coming from the top. From each of the five connections, actually 5 connections are coming from the top. Individual rows are corresponding to the top layer, and the columns are referring to the second layer. Okay, so these are the two element, and this 5 are there. So 5 are belonging to the top layer, and the 2 are belonging to the second layer. So what do? We get the length of how many elements are there in this list. So length k to a, okay, will have how many? Okay, it will be 5, because I'm sorry, where is it? It will be 5 because this many list objects are there inside. Okay, so there is equivalent to the number of layers which are there in the first layer. 5 list objects will be there, and then individually inside them, if I extract this value, only the top value length, okay, this it is having two values. That means all of them below also will have two values, because we are talking about a dense connection, and all the output layers will have anyway input coming from the top. So we can assume if you have the length of this one list, first list, it will be the same for the remaining list. So I am extracting out the length of each element, and then I'm going to flatten it out. So get the, and I need to take care of the last layer. I have to add f to it. So I am only extracting out the first 4 here, and then the last one I will defer it next time. Okay, so that I am running it as a separate loop, so that I can extract out the last value that I am getting here. I need to add an f and then put a closing parenthesis. So I separate it out like this. I get a list object first, this first list object, and then I get the length of the list object and print it out. So we are flattening it out. Then next list object I take and then extract the value. So you take the list object j, which is the index into this list object, and extract it out. I am sure you are all expert in Python, so you should be able to understand this very easily. Okay, so once we get this, bias is straightforward because there is going to be only a single layer, and last layer is a very simple one, because what is going to be the last layer, I will show you. It is only two values which is listed like this, and then the bias value is single one. So these are the output we are getting. Okay, now let me show you this. This is the list of 5 values, and then what I am doing is printing it as f. Okay, I have not yet put the parenthesis. That I do it when I generate the C code for it. I am going to generate a header file for it. That time I will use this code to put it inside a flower parenthesis and then close it after this. Okay, so we will be using this code. Okay, I want you to understand this code clearly today, so that tomorrow what we will do is we will understand the code which will extract out and generate a header file which will be used in our ESP32. Okay, so once you understand this clearly, I will go to the C function and then explain you on ESP32 how are we going to use this arrays to inference to perform the inferencing on the model. Okay, so that's the plan for tomorrow, and that's what I want to explain it to you today. What is this? This is that is the day after tomorrow. Tomorrow is holiday. Huh? I didn't know. You guys are giving me shock every day.
No, sir. Sir, Wednesday.
Wednesday is holiday, no? Okay. Ambedkar you are advancing his birthday by one day. Okay, is it clear to you what I am trying to explain? Hello, guys.
Yes, sir.
Okay. If Sandeep is clear, let me assume that everybody is clear. Okay. It's not very complex, very simple. I will share the code to you today itself, and then please understand this. We'll use it for generating a C file tomorrow. Okay. Let me save the attendance before I go.
Sir, will we be doing matrix multiplication in C? Kind of.
No need to do actually.
It will directly generate us this C-like file.
See, okay. What I will tell you what is planned for tomorrow. Similar to the matrix multiplication, we'll be doing it in C. What we will be generating from Python, okay. Maybe you can also try doing it. Header file. We will be generating a header file. Let me show the header file to you. Okay, it's not a surprise. Okay, where it is to. Okay, this is the generated C file, okay, that we'll be seeing tomorrow. So we will also output the characteristics of the model, which from where you have taken it out. Okay, we'll also generate the models versions that we have used. Okay, then we'll output the size of the layers that we have. Well, one thing is it is assuming as a 2-layer. Okay, the model is only 2 layers. For 3-layer, I want you to write a assignment. So this is the output we are going to generate. Okay, this whatever I showed you, this thing is all header. This is the 16 values. We will terminate it with this. Okay, so W1 data, bias data, W2 data. This will be 256 values because 16 by 16, and then this will be 16 again, bias 2 for the second layer. Last one, weights are only going to be 16 because output will be connected to the one output layer, and the last bias will be this value. So this is the generated header file. Okay, and then we will use this array to whatever input we get, we will multiply it. You do a small you can call it as a matrix multiplication, as a scalar multiplication in a for loop. Okay, it's not a pure matrix multiplication. We don't need to do a individual output only we are going to multiply. Okay, we don't need to do a matrix multiplication because every output that you are getting from the top layer, you need to multiply with the weights of different values. So I won't call it as it's all scalar multiplication only we'll be having, but we will be doing it with a matrix. Okay, it's not between two matrices.
Sir, this is you have written it up. Some program has generated this first.
No, this is a generated program which I wrote it. Okay.
Okay.
It's a generated header file from the Python code that I wrote in using the same logic that I have explained you today, because we are only thing is extracting out is the difficult part of the thing. Then generating the header file will be a little more laborious, but it is not too difficult. Okay.
Sir,
yeah, go ahead.
Sir, this can be good for dense layers, like because those are nothing but if we can imagine they are sort of a matrix multiplication type. But if we go towards like CNN, we were talking about during the in the beginning of the class of this semester, then how we will be doing it, because they are
No.
not simple.
Yeah. Good question. We will not do this. This I am doing it only for a demo purpose to make you understand how exactly internally the sequential model or any weights are maintained, and then how we can use it in the inferencing in C code, just to tell you how exactly the model behaves and then what exactly is happening. Okay. So to answer your question, classification model, classification problems and CNN, we will not be doing this. It is not going to be even humanly possible to do that. We will be using TFLite. Okay, that I will do the TFLite in this itself. Okay, with the sequential model, then classification model also you will use TFLite only. In once you use TFLite, you don't bother about internal layers and weights and all that. Okay, I hope it is clear.
Yes, sir.
Okay, so you have class. Okay, bye bye.